Hi, everyone. Well, now that we have the 10 properties and are able to talk about linear combinations, the next two topics we talked about was spanning and independence. So we're going to use the exact same definitions and we'll have all the exact same results. It's just that we're using slightly different objects. So the span, if you give me a bunch of vectors in the vector space, then the span of those vectors is the set of all possible linear combinations of those vectors. Notice that pretty much by definition, if you look at P2, the set of all polynomials of degree 2 or less, that is spanned by the vectors 1, x, and x squared. Because just it's immediately that every polynomial that's degree 2 or less is written as a plus bx plus cx squared. And that literally is a generic linear combination of the vectors 1, x, and x squared. So we have at least it's spanned by those things. I drew another one. Notice that if you look at the set of all 2 by 2 matrices and form these 4 vectors, these vectors being 2 by 2 matrices, that any 2 by 2 matrix can be written as a linear combination of those 4 matrices by just looking at the combination I just wrote out for you. So then M22 is spanned by these 4 vectors in M22. You have to be careful though. See, linear combinations require finite number of things. You only add a finite number of things. But when I looked at the spanning set of all polynomials, the spanning set for all polynomials is all vectors of the form 1, x, x squared, x cubed, x to the third, x to the fourth, x to the fifth, and so on. Every polynomial needs a finite number of those as a linear combination to get added to be your polynomial. But notice that the set that spans the space is not finite. It's infinite. So then when you form the linear combination, it's adding up a finite number of things. But if you go and look at the spanning set, it doesn't need to be finite. It could be infinite now. Also from Calc 2, notice that this automatically then prevents you from doing things like from power series. You know that 1 over 1 minus x is 1 plus x squared plus x cubed forever. That is not a polynomial. 1 over 1 minus x is not in the set of polynomials because polynomials have a finite number of terms. So this is like polynomial-like, but it's not actually in the set of polynomials. This would then be an infinite linear combination, which is beyond this course entirely. Like we're talking about really advanced stuff. That's beyond this course entirely. All right, so then just like we did before, you might wonder, is something a linear combination of a particular given set of vectors? You could be asked that question as, is a vector in a certain span? So the work is exactly the same. There's nothing magic here. It's the exact same work as would have been taught before. I want to know, is the vector R in the set P2 in the span of the 2 vectors P and Q? If you want to say the polynomials and say vectors, it's fine. To check that, it's literally just a matter of writing it down. So then let's see, can we find 2 scalars? So C times Px plus D times Q of x, that will equal R of x. Well, literally just write everything down. So then you get C times 1 minus x plus x squared plus D times 2 plus x minus 3x squared. Will that equal 1 minus 4x plus 6x squared for some choice of C and D? On the left-hand side, just add up like terms. You would then get C plus 2D, the constant, plus. You would then get D minus C, or if you want minus C plus D, times x. You then have plus. I'd have C minus 3D, that has to equal times x squared. That has to equal 1 minus 4x plus 6x squared. Well, if these 2 polynomials are equal, from what you learn from polynomials are uniquely described by their coefficients. This means instantly that 1 plus 2D has to equal 1. That means negative C plus D, that's got to equal negative 4. You have also that C minus 3D, that's got to equal 6. And notice that the question of determining whether these 2 vectors in this span, in this weird space of polynomials, it actually breaks down to a problem you've seen before. There must be some really strong connection between what you've been taught previously in the past 5 chapters and the materialists just in this one extra chapter 6. If you just try solving that, so if you just quickly try to solve that, I think you can pretty quickly see that the D here is going to be, oh boy, what would it be? If I add these together, what would I get? You would get 3D equals -3. So D must be -1, which means that C has got to be 3. And actually that satisfies all of them. So yes, the answer is yes. Because if I take 3 times P and I subtract 1 times Q, I get R. And this is a function of X. If you want to write with function notation, you can. So yeah, it actually is in the span. Now, another question you were given way back when was, does a set of vectors in R3, R2 span R2 or R3? We can ask the same questions here, and it boils down pretty much to the exact same type of computations we did back then. I want to know, do these 4 2x2 matrices, do they span all of M22? If they do span all of M22, that means if you take any matrix in M22, we'll call that A, B, C, D, it would have to be written as a linear combination of these. That means then there has to be scalars, C1, C2, C3, C4, so that the linear combination formed with these scalars would equal A, B, C, D. Literally now just take the left-hand side and just add it all up. You take the left-hand side and add it all up, you get this 2x2 matrix. Well, you remember though that 2 matrices are equal if and only if the entries are equal, because there's this uniqueness that we use. That means that this has to be true. Once again, notice that we get a linear system in C1, C2, C3. And the question is there a solution, right? For every A, B, C, and D, is there a solution? We don't care if there's more than one solution. We just want to know there is a choice for C1, C2, C3, and C4, so that for those choices, all these equations are true. Well, but then if you look at that system, you can think of that as this matrix multiplication, this same thing, but in matrix form. And we want to know then that given this vector, can I find this solution? And well, that particular matrix is invertible because its determinant is not 0. So then it has a solution. Therefore, yes, these 4 vectors, these 4 matrices actually do span all of M22. Okay, one more example of doing this, you have to be careful with function spaces. See, when you write down a linear combination with functions, it's understood to be of X. That means that you write down an identity. It's something that's true for every X, not 1 or 2, every X, for every input. The left-hand side, the linear combination, equals the right-hand side, the target function. So for example, the function, the sine of 2x is not in the span of the sine of x and 2x. It's not in the span. Yes, the sine of 2x can be written in terms of sine of x and cosine of x. That's the double angle identity, but not using vector addition only and using scalar multiplication only. It would require function multiplication, which we don't have. So here, to show why, let's just pretend it is. Suppose it was, and I'll show you how things go wrong. Suppose so. Then their scalar C1, C2 exists. So C1 times the sine of x plus C2 times the cosine of x has to equal the sine of 2x, and that's for all x. For all x. Okay, well then I want to have a relationship between C1 and C2 only. If x equals 0, this results in that the C sub 1 times 0 plus C sub 2 times 1 would equal 0. So then C sub 2 has to be 0. But if, on the other hand, that x were to equal oh, let's pick another good one. Let's say pi over 2. This results in, you get c sub 1 times 1 plus c sub 2 times the cosine of pi over 2, that's 0. You then have the sine of pi, which is 0. So c1 would have to equal 0 also. So that implies that the sine of 2x is always 0 for all x, which is clearly wrong. Which is clearly false. So therefore, that means that the sine of 2x is actually not the span of the sine of x and the cosine of x. Again, be very careful. Be very careful with function spaces. You can only use addition of functions and scalar multiplication, nothing else. Nothing else. Another good question here for students would be, hey, is the tangent in the span of the sine of x and the cosine of x? The answer is no. No, it's not. The tangent is the division of sine and cosine, but you can't do function addition. You get function addition, scalar multiplication only. All right, good. Last thing. So then the one thing I've left out of all this is, well, if you have a span of vectors, what's so special about it? And before, I proved to you back when we first introduced way back when in Rn spaces, the span of a bunch of vectors is always a subspace. That means then that if you can ever show that a certain set of objects is a span of a bunch of vectors, it's automatically a subspace. And you don't even have to check all 3 properties. You only have to now check just one. Is it a span of something? Also, when you have a bunch of vectors in a set, if it's going to be a vector space, that means any linear combination of those objects has to be in the space also. That means instantly that the span of these objects is the smallest subspace that contains it, because every subspace, every vector space that contains the vectors v1 to vr has to contain every linear combination of them also, and therefore contain the span of them. So we did this problem before, one like it. I want to show the set of all polynomials a plus bx plus ax squared is a subspace of P3. Notice that to be a subspace, I don't have to have a polynomial of 3rd degree. It just has to be contained inside the set of polynomials of 3rd degree. This is clearly a span. So this is the span of, it's 1 plus x squared because right here, and x because right here. It's literally just a linear combination of those 2 things. It's the span of those 2 things, so is a subspace of P3. It's actually a subspace of P2 also. It's also a subspace of all the functions of all continuous functions. It's a subspace of all the differentiable functions. It's a subspace of just the functions. It's a subspace of lots of stuff. And that's it. That gives you a good quick introduction to linear combinations and spannings. The next thing we do is independence. But that's another video. I think it's enough for now.